Star orbiting a black hole, predicting forces. The objective of this lab is predicting the mass of a black hole around which a star is orbiting, studying the forces involved. First of all, let's take a look to the data. The data includes the X and Y position of the star. If we represent the data, we can see that the star makes an ellipse around the black hole. If we come back to the raw data, we can see it has a period of around 900 days. So we have a star similar to the Sun orbiting a black hole, the main distance 80 times greater than the distance from the Earth to the Sun, and with a period of around 25 years. Comparing with our own solar system, that means that the period is similar to Saturn but twice the distance, or almost the same distance to Uranus but with 1/3 of the period, or with a similar average speed to Mars, although Mars is 12 times closer to the central object. We introduce the mass of the star into the model, read the data, and calculate the net force, the perpendicular force, and the parallel force. They are represented in yellow, blue, and black respectively. As can be seen, the net force always points from the star in red to the black hole in black, and the strength of the force decreases with the distance to the black hole. To find the mass of the black hole, we have used the gravitational force that affects the star. And we have found that it's only 10 times greater than the mass of the star. If we calculate the mass not only in the last point but in all the points, we can see that we got always the same result. If we choose one of the points of the orbit and we represent points every 1 year, we can see that the net force is pointed to the black hole. The perpendicular force makes the star deviate from the straight line to the black hole side, and the parallel force changes the velocity magnitude. The star orbits clockwise, and as can be seen in the time represented, the star travels longer distances in the same time, while its distance to the black holes reduces. According to Newton's second law, the net force is the derivative of the momentum respect to time, but we have used an approximation, evaluating the variation of the momentum with time. The whole orbit takes around 25 years. As the space of time is 1 day, it represents more than 900 points. As we can see in the image, this means that the points are very close, so consider the variation of the momentum similar to the derivative seems rational. But what would have happened if we have used time step of 1 year to calculate the net force? That means use points separated like we can see in this image. If we run a simulation representing the two calculations, we can see that both are quite different. In red we can see the one with 1 day separation, and in blue the one with 1 year separation. As can be seen, with 1 day the force points to the black hole, while with almost a year the force doesn't point to the black hole. So using a time step of 1 year doesn't represent well the gravitational force of the black hole, but using 1 day it seems quite reasonable. So the difference between the net force and the variation of momentum with time becomes greater with greater time steps. So to be more accurate, we need very tiny time steps. We would have found similar differences with the perpendicular and the parallel components of the variation of momentum and the net force. What if we change the black hole but the motion remains unchanged? Same motion means same forces in all the orbit. We don't change the star, neither the distance to the black hole, neither the velocity of the star as a vector. Then the black hole has to have the same mass than they calculated previously. In fact, any object with that mass, like a massive star, will give the same orbit.